Dear all, welcome to the playlist of sensors and transducers. In this session, I'll be discussing linear variable differential transformer. It is also known as LVDT. Let us understand the concept of LVDT. What do you mean by LVDT? We can have a brief discussion on LVDT. LVDT is a linear variable differential transformer. It is an absolute measuring device that converts linear displacement into electrical signal through the principle of mutual induction. Okay, that is a main principle of LVDT. And also, it is a passive transducer. Why? Because in order to operate, it requires an external excitation. That is why it is known as passive transducer. Okay. It is commonly employed for measurement of force, then weight, pressure, acceleration, etc. These are the mechanical quantity. You can able to measure force, weight, pressure, etc. in terms of electrical voltage. In terms of amount and the direction of displacement also, you can able to measure the quantity as well as the direction. Okay, because force is a vector quantity, it is having both magnitude and direction. You can able to measure the magnitude and direction. In fact, the LVDT comprises of one primary winding, then two secondary windings. Apart from that, there is a magnetic core. It should have a magnetic core. If I talk about the secondary windings, okay, let us consider S1 and S2 are the secondary windings, which is having equal number of turns. That point you have to remember, but which are connected in series and opposite direction. That is a speciality. And EMF induced in S1 that is equal to E1 and EMF induced in S2 that is equal to E2. And if I look at the nature of EMF, both are 180-degree out of phase. That is another speciality because they are connected in opposite manner. Okay. And what about the primary? We have to provide suitable excitation to the primary source. Otherwise, this transducer will not operate. You know that this is a passive transducer. Definitely, we require a primary source. It obeys the principle of mutual induction. Okay, these are the basic information regarding LVDT. Now let us understand the schematic diagram of LVDT. You can able to see two diagrams, figure A and figure B. Let me look at the figure A. Here you can able to see we have a primary winding. Okay, this is your primary winding. And we have two secondary winding. Okay, this is the first secondary winding and this will be the secondary winding. So both are connected in serially and also which is in opposite direction. The EMF will be 180-degree out of phase. Okay, the next component is movable core. There is a movable core which is directly connected with the mechanical object. And figure B, we can able to have a elaborated manner of figure A. This is the elaborated diagram of figure A. So we have the primary. Okay, we have the primary source and we have the secondary. Okay, we are having the secondary winding S1 and S2. If I look at the number of turns, both are equal. Okay, and E1 and E2 are the EMF. And the nature of EMF that will be 180-degree out of phase. And this is your output voltage. And your mechanical object that is directly connected to movable core. Okay, with respect to the mechanical movement, the movable core is also going to operate. And also you can call LVDT as an electromechanical position transducer. So that is another specialty of LVDT. Okay, so familiar the diagram. Now we have to explain how does it work. That's very important. You know that this is a variable inductance transducer. So we must know the operating principle carefully. So you can able to see another diagram. It is similar to the previous diagram only. We have the moving core. Okay, mechanical body is connected to the moving coil. Okay, moving core is available here. And we are having the primary winding and two secondary winding. Then the output of the secondary winding is connected to output voltage. Practically, your LVDT look like in this manner. Okay, this is the practical availability of the LVDT. It's available in the website. You can able to order LVDT for your desired application. IndiaMart.in and many more websites are available. You can able to make out. Okay, so this is regarding LVDT. Now let us understand how does it work. That's very important. Okay, so the whole working has been divided into three segments, case 1, case 2 and case 3. First and the foremost, let us look at the particular diagram. Figure B, you can concentrate the figure B. Now, the position of the movable core is at the mid of S1 and S2. It is at the middle of the secondary winding, exactly middle of the secondary winding S1 and S2. Okay. Anyway, you know, this is basically operate based on the principle of mutual induction. Whenever the movable core, I'm talking about case 1, whenever the movable core is at the middle of S1 and S2, the EMF, both the EMF induced at S1 and S2, both are equal. You can say that E1 equal to E2 for the first case. This is actually case 1. Okay. Now what is the value of differential output? So V0 is equal to, how can I write? E1 minus E2. What is the value of E1 minus E2? Because both the magnitude are equal. Therefore, the EMF induced across V0, differential output, that is equal to E1 minus E2, that is nothing but 0. Okay, whenever the movable core is at the exact middle position of S1 and S2, I have to say that output voltage is equal to 0. That means you can understand the position of the movable core. It is at the middle of those particular coil S1 and S2, winding S1 and S2. Okay, that is the first conclusion from the case 1, first case. I hope you understood. Now let us understand remaining two cases. I would like to explain case 2. You know that the movable core, you can able to observe the movable core. The movable core is moving towards this particular coil. Suppose the movable core, it is moving towards the particular coil S2. At that moment, E2 will be greater than E1. Okay, E2 is greater than E1. So obviously that will happen because the movable core is nearby this particular S2. Okay, therefore the EMF induced at the second coil is greater than the first coil. Therefore I can write E2 greater than E1. So what about the output voltage? Output voltage must be E2 minus E1. Okay, E2 minus E1. So you will be getting a certain amount of EMF. Okay, so that you can able to understand that the movable core that is nearby this particular second coil, that means S2, movable core is nearby S2. That is why you will be getting the output like this. Okay, this is the second case. So that you can able to understand the displacement, velocity, everything you can able to measure. Distance, displacement, etc. can be easily measured. I would like to explain the third case. Moving on to the third case. Suppose your movable core, you can able to relocate the movable core. Suppose your movable core is nearby S1. At that moment, E1 will be greater than E2, where E1 is the induced EMF which is generating across S1. E2 is the induced EMF generating across S2. So E1 will be greater than E2. Now let me know what is the differential output. Differential output is nothing but E1 minus E2. This is the third case, E1 minus E2. Okay, so that we can understand that the position of the movable core that is nearby the first secondary winding, that is S1. Okay, so that you can able to identify where is the position of the movable core. With respect to that, you can able to determine distance, displacement, velocity, etc. Okay, so this is the way how LVDT operate. Okay, you can refer any of the diagram. Okay, all the diagrams are same only, but the representation is different. So three cases I have written. In the first case, the induced EMF output to voltage will be 0. Differential output is 0. Second case, differential output is E2 minus E1, and we can understand that the movable core is nearby S2. In the third case, we can say that the movable core is nearby S1, so that we can able to write the differential output as E1 minus E2. Clear? So these are the peculiarity of LVDT, and we have understood the working of LVDT. So this is another diagram which is depicting how it is going to operate. Look at the middle diagram first. So where is the position of the core? Position of the core is at the middle of S1 and S2. Therefore, the output voltage is absolutely 0. Moving on the left side, let us look at the left side diagram. Your core that is nearby S1. Okay, therefore, the differential output is equal to E1 minus E2. So we can understand that core is nearby S1. Moving on to the third diagram. Look at the third diagram. Your core is at the near position of S2. Therefore, we can write that EMF output or differential output is equal to E2 minus E1. Thus, you can able to understand the magnitude and the direction of the particular moving body by using LVDT principle. Same thing I have written over there. See, the amplitude of differential output voltage determine the distance traveled, and the phase of the output voltage indicates the direction traveled. It is very clear. And if I look at the waveforms of LVDT, you can able to observe that for a certain extent. Okay, so please refer the diagram. For a certain extent, for example, from this point to this particular point, the scale is actually linear. Afterwards, scale is becoming non-linear. The graph shows the output voltage versus the range. Okay, position. For a certain extent, it will be linear. See, from this point, this is linear only. Linear. But once it is crossed that limit, it becomes non-linear. That is a speciality. Okay, this figure depicts the operation. Okay, whether it is in linear operation or non-linear operation. We can say that for a certain extent it becomes linear. After the specified range, it becomes non-linear. So that is the conclusion which we can understand from the diagram. Okay, so anybody asked about Viva regarding will the scale of LVDT is linear? Okay, you can say that for certain range it is linear. After beyond that particular limit, it is not linear. Same diagram I'll be representing in another manner. See the graph. That means the output voltage versus full range. That means core displacement. For example, the core is at different position like 0%, 50%, 100%. Whenever it is at a certain range in between 0% to 100%, it shows the linear scale. After that, it is going beyond the linearity. That means there is a non-linearity which will be present over there after the certain range. The curve is linear for small displacement, and beyond this range, it starts deviate from the straight line. So that is the conclusion which we can make from the particular diagram. I hope you are following. Okay, it is very clearly visible. At a certain range, it is linear. Okay. Now I would like to discuss about the constructional details about LVDT. So you can have a look on the particular diagram. So this is a diagram which are concerning for LVDT. First point, the transformer comprises of three coils. That means one primary. Where is the primary? You can directly observe that one primary winding. This is one primary and the two secondary like S1 and S2 that I have written over there. It is wound on the hollow form. It is very clear. The shape look like a hollow form and which is typically made up of glass reinforced polymer. It is made up of glass reinforced polymer. The coil are arranged such that primary coil is located between two secondary coil. It is very clear. Primary coil which is located between two secondaries. Okay, you can refer two secondaries where primary is locating in between two secondaries, which are symmetrical. Obviously, it is symmetrical and wound in series but opposite direction. And therefore, you are getting the E1 and E2 out of phase each other. And also the core is made of magnetically permeable material. Okay, maximum amount of flux has to be transferred. That is why it is made up of high permeable material. Moves freely inside the bore of the transformer. It is also very clear. And the moving object that is directly connected to this particular area or particular part. A non-ferromagnetic shaft or push rod is coupled to the core and connected to the object being measured. See, this is a mechanical part that is connected to the shaft or core of the particular LVDT. Okay, where you are supposed to measure the displacement position of that particular object. That is the ultimate goal. That means object is directly connected to that particular core. As the object moves, core is also getting varied. Whenever core is changing the position, EMF also getting varied. Okay, likewise you can able to trace the displacement and velocity of that particular core. The differential voltage in the secondary windings determines the distance moved and the phase of the voltage indicates the direction of movement. This is also very clear. So you can have a glimpse on the construction details of LVDT. Okay. So go through the diagram once again. Just recall the points whichever I explained. Now you can able to understand that one of the application of LVDT, pressure measurement is possible by using LVDT. So this is your external body. External body which is exerting certain amount of pressure that is directly connected to bellows. Okay, it will directly coupled with that movable core. With the help of bellows, it will be linking with the movable core. As the pressure increases, the position also varies. With respect to the position, you will be getting the different. This is the primary supply. Primary will be applying to the coil. And with respect to the position of the movable core, you will be getting the output voltage. That is very clear from the diagram. And also you can able to measure the displacement by using LVDT. See, I would like to measure the displacement of a particular object. That object will be connected to the core part of the LVDT. Whenever the object moves, core is also getting varied. So based on the position of the core, you will be getting the output voltage. So here normal case output voltage is 0 whenever core is at middle position. Whenever core is nearby ES2, secondary winding, the second part of the secondary winding, then you can able to write ES2 minus ES1. That is the differential output. So whenever core is nearby the first winding of the secondary part, ES1, okay, this particular S1, then you can write EMF is equal to ES1 minus ES2. Likewise, you can able to determine the displacement. What are the advantages of LVDT? As you can observe, these are the following advantages of LVDT. It gives high output, no need for intermediate amplification. and it ensures high sensitivity, almost 40 volt per millimeter. That means for 1 millimeter, you will be getting 40 volt at the differential output. Low hysteresis, so that hysteresis loss will be reduced. Excellent repeatability. You can do n number of operation, it won't disturb. Okay, then less power consumption compared to other type of transducers. Less friction and noise. Okay, that is another added advantage. Tolerate high degree of shock and vibration because it is connected with the moving body. Definitely, it is having the ability to shock the vibration and high operating temperature. It is in the range of minus 265 degrees Celsius to 600 degrees Celsius. Then radiation resistant design. So that is another peculiarity. Therefore, it can be employed in the operation of nuclear power plant. That is another viability of LVDT in the area of nuclear power generation. LVDT devices are extremely robust and rugged construction. Okay, since there is no physical contact, therefore no friction, no wear and tear, etc. So these are the another added advantages of variable inductance LVDT type transducer. Okay, you can able to note down these particular points, but we have to face certain cons. What are the main drawbacks of LVDT? The drawbacks of LVDT, a few drawbacks of LVDT are as follows. These are transducers sensitive to the stray magnetic field. Because of that, you will be getting the wrong measurement. Then relatively large displacements are required for measuring the differential output. If the displacements are very less, you won't get the output. That's a problem. Even though there are displacement, but you are failing to get the output. That's a problem of LVDT. Drawback. Receiving the signal must be AC and the demodulated network should be used if DC output is selected. That is another constraint. Then performance of transducers affecting by the vibrations and LVDT is not suitable for very fast dynamic measurement. That is another setback of variable inductance LVDT type transducers. The performance of LVDT is affected by the temperature. So you can able to operate only the certain range of temperature that I have already shown you, the certain range of temperature. See, so this is only the way to maintain that particular LVDT. Beyond that, you cannot able to maintain. Okay. What are the applications of LVDT? So we are having few applications like automation control system in the area of automation, especially if you are using PLC and SCADA type operation. Okay, if you wanted to implement that, definitely LVDT presence is required. The presence of LVDT is required. Moreover, for the operation of hydraulic sensors and pneumatic sensors, the presence of LVDT is truly unavoidable. And it can be used in accelerometer or you can call speedometers, okay, to identify the position. Then it will be used in jet engine control, and finally it is used for measurement of material thickness. These are the few applications. You can list many more. Why? Because it is a highly useful sensors in the all the area of automation. So you can able to see the practical views of LVDT. So different series are available: LD320, LD500. Likewise, you can purchase. I have referred the following textbooks to gather the information. In this session, I have discussed about how does LVDT operate, what are the construction details about LVDT, and what are the pros and cons of LVDT. Finally, I have listed the certain applications. If you are having any queries, you can put up in the comment box. Surely, I'll revert. Finally, thank you very much for watching this video.